Okay, so it should be visible now, and you should be able to hear me. Ah, great. Okay. I propose I'll just jump right in. Okay. So, hello everyone. My name is Simon Vandevelde. I'm a PhD researcher at KU University, the EVICE Research Group in Belgium, um, and I will be presenting the work I do today together with Bram Aerts and Joost Vennekens called "Tackling the DMN Challenges with cDMN: A Tight Integration of DMN and Constraint Reasoning." So first, I will go over DMN. What is DMN? Then I'll talk about cDMN and I'll show some examples. We'll compare the two, and then at the end, I'll conclude. So first, DMN. For those of you who don't know, DMN stands for Decision Model and Notation Language, and it's a notation standard for modeling decision logic, which is published by the OMG group, the same group that publishes, of course, the UML language. And it uses table-based representations of decisions, and it groups these together in decision requirements diagrams, with the main focus being readability and traceability of the models so that they're user-friendly. So here's an example of a decision requirements diagram, which is used to calculate the amount of vacation days an employee has. So here, the DRD represents the structure of decision models. So every square you can see is a decision which is made. These are inputs, and we can link them together in a DRD. So every square is a decision table, and in a decision table, we decide our outputs here in blue based on our inputs here in green, where every row represents a rule and every column represents a value. So, for instance, age, the constant age would represent the age of an employee. The behavior of a decision table is defined by the hit policy. So, in this case, this would be the unique hit policy. Um, and this table is read as if the age is less than 18, then the years of service doesn't matter and eligible 5 is true. If the age is between 18 and 60 and the years of service is less than or equal to 10, then eligible 5 will be no. And this is how the tables can be read in a user-friendly way. In these cells, we use sfield as inputs, or we can use normal field or sfield as inputs. And what that is, it stands for simple, friendly enough expression language. And this allows us to input simple values, lists of values, numerical comparisons, ranges of values, and calculations in the cells of input columns. So throughout this presentation, I will be showing some examples, and these examples are all taken from the DM community website, which is a website about DMN, and they post monthly challenges with varying degree of difficulty, which are meant to explore the boundaries of what DMN can and can't do. And the challenges which I use in this presentation are listed at the bottom, so you can look at those later if you'd like to. So cDMN and some example. What is cDMN? cDMN is a notation language which we made, which stands for Constraint DMN. And basically, we extend DMN with constraint reasoning and other related concepts, such as quantification, types, functions, relations, optimization, and more. And this allows us to model more complex decisions and model other decisions more simple. So we introduce 4 new tables in total, namely the glossary, constraint tables, data tables, and the execute table. I will go over each of these tables one by one now. In normal DMN, every value is a constant, as I've shown earlier. In cDMN, we extend this by also adding types, relations, booleans, and functions, and we define these in our glossary tables. So, for instance, we have the glossary type, in which we're able to define a type person, which consists of strings, and these strings are Agatha, Butler, and Charles. And we have a type number, which is an integer between 0 and 100. We can also define relations, which are, relations between one or more types, where here, for example, we have the relation person hates person, where we can, for example, express that Agatha hates the butler or butler hates Charles. We also have the Boolean glossary, in which we're able to define Booleans. Then there's the constant glossary. Here we define constants as they work in DMN, except that we always have to type them. For instance, here it's of type person. So this means that the killer, the constant killer, is always either Agatha, Butler, or Charles. And then we have the function glossary, in which we define functions. And a function is a mapping of a type on another type. So For example, here we have age of person, and this will map every person on their age, and this age is a number. Then we also add constraint tables. So in normal DMN, a decision table, as I've shown earlier, has the following characteristics. It uniquely defines the output. There's only single values as output allowed, and if there is no rule applicable in a decision table, it will default to null value the output. In a constraint table, we do things differently. Namely, in the output, we allow a range or a set of values, so there's multiple values possible. We allow sfield in the output. There's no default, so we don't say anything when no rules apply, and every constraint table represents implications. We also extend this. Oh, sorry. This is an example of a constraint table where, as you can see, this is denoted by the E asterisk hit policy, so the every. And in this table, we state that if require healthy is yes, then total sodium, total fat, and total calories need to be below these values. But we don't say anything when require healthy is no. Then these values can take on, or these constant can take on any values. We only say something in the case that require healthy is yes. And this can be translated to first order logic as such. We also add quantification in cDMN, and this allows us to apply rules over all elements of a type. So this also allows for more flexible and compact tables. For example, in the map coloring problem, where we have a map and we want to color it in such a way that no two countries share the same color, we could simply say that for every country called C1 and every country called C2, if they border, then they cannot have the same color. Another thing we add in cDMN are data tables, and we do this based on the theory that typically problems can be split up into two parts, where on one hand we have the general logic of the problem, and on the other hand we have a specific problem instance to solve. So for example, for the map coloring problem, our general logic would be that two bordering countries cannot share a color, and that every country needs a color. But our specific problem could then be a map to color, for example, Western Europe. So in cDMN, this logic, we would decode it as decision and constraint tables, whereas this problem instance we encode as data tables. So a data table does not have a hit policy, but rather it has data table in the name. We only allow basic values inside of a data table, so no complex field. But quantification is still possible, and this allows us to do the following. We could, for example, say that for every country called C1, which is Belgium, and every country called C2, which is in this list, they border. And then we could do the same for Germany and all the other countries. And then we'd have a data table representing a concrete problem to solve. If we ever want to color in a different map of the world, all we would need to do is change out this data table by a new data table representing this other part of the world. Then we also add the execute table. And this is because in a DMN model, there is always a unique solution for every set of inputs. Now in cDMN, this is no longer the case. cDMN usually defines a solution space where there are multiple solutions to pick from. And the execute table allows us to define what solution we want. For example, we could say get one model or get 5 models or etc. Or we could ask for all the solution using get all models. Or we could also optimize a value by, for example, saying maximize the score or minimize the score. So find me the solution in which the constant score has the highest or the lowest value. So in summary for cDMN, cDMN stands for constraint DMN. We add constraint reasoning and more to DMN. We do this by adding 4 tables in total, and we don't define a single solution, but rather a solution space. So if we compare this to standard DMN, so this is a map coloring solution in standard DMN. And as you can see, this table is very difficult to read, especially for laymen. That's the entire point of DMN, being able to read it very easily without having to have this complex knowledge of how programming works. So here, the DMN table completely misses that target, but it is a valid DMN table. In cDMN, as I've shown before, we would do this as follows. We would state that for every country called C1 and every country called C2, if they border, they cannot have the same color. And this table replaces that previous table with just way simpler. Another example, and here we compare to a solution in OpenRules, which is a tool that implements a DMN-like notation, for Who Killed Agatha, the challenge, where there's the rule that states that the killer hates Agatha and is not richer than her. So in OpenRules, this is implemented as follows. If the butler killed Agatha, then the butler hates Agatha. If the butler killed Agatha, then the butler is not richer than Agatha. And we do this for every person. And of course, this has a scalability problem. If we have more people added to our list of suspects, then this table will continue to grow and grow, and we need to update our model accordingly. In cDMN, however, all we need is a simple constraint, which states that the killer always hates Agatha, and the killer is never richer than Agatha. And this does functionally the same as the table below, except smaller, and it doesn't need to be updated if more people get added. Another example, this time an implementation in Corticon, which is also a tool that implements a DMN-like notation. For the monkey business challenge, we have a rule that says monkeys do not share fruit or their place. And in Corticon, this is encoded as Mike's fruit is not the same as Sam's fruit, and Mike's fruit is not the same as Harriet's fruit, etc., etc. And the same for place. And again, we have a scalability problem. Whereas in cDMN, we would implement it as follows. We would say, for every monkey called M1, and every monkey that is not M1, their places cannot be the same, and their fruit cannot be the same. Again, in a simple constraint table, which replaces these two tables. And if more monkeys get added to the problem, we do not have to update our model or update this table with more information. Another example, again in Corticon, for the hamburger challenge, which is a challenge in which we need to construct a hamburger, and we have some constraints. For example, a rule says that the sum of sodium and calories of all ingredients have to be lower than 3,000, and the total fat has to be lower than 150. In Corticon, this is implemented as follows. We count every ingredient, we multiply it by its nutritional value, and then we state that it needs to be below a specific value. Now, this has, of course, multiple downsides. First of all, it is difficult to see why some things are done in the same that they are done in the way that they are. For example, here, why is it 3 plus 160? It's not easily an easy thing to see. Furthermore, if we ever change our nutritional value by, for example, taking a new ingredient, having a healthier beef patty, we would have to update this value in every formula. Now here it's fairly simple, but if it's a large formula, this isn't very user-friendly. And furthermore, say that we want to apply this problem to a different recipe, so we don't want to make a hamburger, but we want to make sandwiches, for example, then we wouldn't be able to reuse this solution. Now in cDMN, we would encode it as follows. We would say that for every item, the total sodium is the sum of the number of every items times the sodium of every item. And we do the same for total fat, total calories, and total cost. And then we simply apply a constraint which states that the total sodium, total fat, and total calories needs to be below these values. Furthermore, we can then, of course, implement our nutritional values in a data table, where, for example, here we say for beef patty what the sodium, the fat, the calories, and the cost is. And this allows us to, one, easily update our data table if, for example, we have a new ingredient or we change beef patties by a more healthier variant. But two, we can also apply it easily to a new recipe by switching out the data table. And another example of optimization here, in the balanced assignment problem, we want to make groups that are as balanced as possible. And we do this in cDMN by stating that for every person P1, P2, if these people are in the same department at their job, but they're not in the same group, then we add 1 to the score. If they are from the same location, but they're not in the same group, we add 1 to the score, etc., etc. And then we simply say, okay, find me the solution where this score is maximized, and then we can conclude that this will be a balanced assignment. And this is something that no other DMN model can, because DMN doesn't support optimization. If we compare our solutions to the other ones that I've shown and more in total of number of cells, then we can find that cDMN is often the most compact. So here the gray means that it is more compact. Moreover, cDMN is able to implement more challenges than any of the other solvers. So to conclude, in cDMN, constraints increase expressivity and flexibility of our models. We can now model more complex models. They're also more compact and straightforward and independent of the size of the problem. So we can conclude that cDMN models are readable, maintainable, and scalable. Thank you for your attention. Are there any questions? Also, you can find my contact information here if you would like to contact me after this presentation.